I did not expect the old railway building on Euston Road in London to trouble me. The official plaque outside the Euston station engine shed, completed in 1837, describes it as an early triumph of Victorian rail ambition, experimental, imperfect, transitional. The kind of place historians explain away with enthusiasm and context. Inside the archives, I began with a familiar image, an 1846 calotype photograph held by the Science Museum, showing early locomotive bays under a vast iron and stone roof. What drew my attention was not the locomotives, but the floor. Beneath the rails, faint in the image, were perfectly aligned circular iron covers, identical in diameter, spaced with mathematical precision. They were not mentioned in the construction logs. No drainage system was specified at this scale in the engineering journals of the time. While examining a folded 1835 engineering drawing by Robert Stevenson, I noticed annotations referring vaguely to subsurface regulation chambers without description. Some researchers studying similar anomalies beneath rail systems describe these as remnants of what they call Tartarian infrastructure, inherited systems repurposed rather than built. At first I dismissed the idea. Then I measured the symmetry. The official narrative is clear. Construction of Euston Station began in 1835, overseen by Philip Hardwick, with engineering consultation by Robert Stevenson. It was Britain's first intercity railway terminus, a prototype by necessity. The story presents innovation born from nothing, Victorian ingenuity creating modern transport infrastructure where only fields had existed before. Yet, a maintenance ledger from 1851, stored at the National Archives, references sealed underfloor access plates, not to be reopened. No explanation follows. The phrasing itself troubles me. Why seal something that was supposedly just installed? Why forbid reopening infrastructure barely 15 years old? I returned to the 1846 photograph. The circular iron covers are visible in 3 separate locomotive bays, each measuring approximately 1.2 meters in diameter. The precision is unmistakable. Identical castings, uniform spacing, and perfect alignment with the building's structural grid. Victorian foundries could cast iron, certainly, but mass-producing perfectly identical pressure-rated plates at this scale, while simultaneously pioneering rail technology itself, raises questions no one seems willing to address. The tolerances visible in the photograph exceed what hand finishing could achieve. Each circle shows the same curved lip, the same bolt pattern, the same surface treatment. I compared them against known Victorian ironwork from the same period. Bridge components, building fixtures, decorative elements. Nothing matches this level of standardization. In the construction journals held by the Institution of Civil Engineers, I found detailed accounts of rail installation, platform construction, and roof assembly. The subsurface systems are mentioned only twice, once in Stevenson's cryptic reference to regulation chambers, and again in a margin note from 1838, stating existing underground provisions adequate for current requirements. Existing provisions. The word choice implies something already present. Some alternative architectural researchers examining regions historically labeled Tartaria on early 18th century maps note similar subsurface infrastructure beneath structures across Eurasia, modular iron systems, hydraulic regulation chambers, and precision cast components appearing in locations separated by thousands of miles. The official histories call these coincidences of parallel development. The physical evidence suggests something more systematic. At Euston, these features are never mentioned in celebratory histories. The building is presented as wholly new, revolutionary, and unprecedented. The infrastructure beneath suggests inheritance rather than invention. Why would an experimental railway require sealed chambers of unknown function beneath its floors? Paddington Station officially opened in 1854. It was designed by Isambard Kingdom Brunel, a man celebrated for pushing engineering limits. That reputation often shields contradictions from scrutiny. An 1852 construction photograph archived at the Brunel Institute shows workers standing atop an already completed subsurface grid before any rails were laid. Beneath them, brick vaulting appeared, uniform and extensive, far exceeding any conceivable drainage requirements. The vaults extend in perfect parallel lines, each arch maintaining identical curvature across a span of over 200 meters. Brunel's surviving correspondence, dated March 1851, describes integration with existing underground conditions without elaboration. The phrase appears in 3 separate letters to the Great Western Railway Board: integration, not construction; existing conditions, not planned infrastructure. The vault geometry is distinctive, shallow arches with equal spans, pressure-optimized curvature that suggests hydraulic function rather than simple structural support. I measured the visible dimensions from multiple photographs: arch height of 2.1 meters, span width of 3.8 meters, wall thickness of 0.6 meters. These proportions match hydraulic galleries designed for fluid pressure management, not the rough stonework typical of foundation trenches. In an 1853 engineering report, Brunel's assistant notes, chambers beneath platform level sealed following discovery of incompatible pressure systems. Incompatible with what? The rail infrastructure had not been fully installed yet. Sealed is the term used in the report. Maps from the early 18th century, including Guillaume de Lisle's 1720 atlas, label vast Eurasian regions as Tartaria, often illustrated with geometric city plans and elaborate transport routes. Some researchers argue these were not speculative but documentary, records of existing infrastructure later absorbed into expanding European empires. The subsurface systems at Paddington, with their modular design and hydraulic sophistication, match patterns these researchers identify as characteristically Tartarian, reusable, pressure-regulated, built to tolerances that suggest advanced metallurgical knowledge. Paddington's official explanation calls the vaults supporting structures. I examined foundation systems from other buildings from the 1850s across London. None show this level of underground development. Liverpool Road Station, opened in 1830, predates most British rail infrastructure by years. As the world's first purpose-built passenger railway station, it should represent crude experimentation. Instead, early photographs reveal foundation stonework of disturbing precision. An 1831 engineering report described the foundation as unexpectedly sound, requiring minimal adjustment to accommodate railbed installation. The stone blocks beneath the tracks show machine-level tolerances, perfectly square edges, uniform dimensions and surfaces finished to a flatness that hand tools of the period could not achieve. I studied an 1829 survey photograph showing exposed foundations before platform construction. The blocks measure uniformly 1.2 meters in length, 0.6 meters in height, and were fitted together with gaps of less than 2 millimeters. No mortar appears between many stones. They were precision cut to fit directly against each other, a level of precision. Beneath the track beds were stone corridors, visible in an 1832 maintenance sketch held by the Museum of Science and Industry in Manchester. These passages ran parallel to the rail lines, approximately 1.8 meters in height and 1.2 meters in width. During renovations in 1895, the corridors were filled with rubble and sealed. A margin note in the renovation ledger reads, "Obsolete voids removed for structural simplification." Obsolete implies prior purpose, function that had ended. But the station was still operating. What function had these underground passages served that was no longer needed? Alternative historians studying Tartaria note that such subsurface corridors appear beneath structures across regions once mapped as Tartaria, from the Urals to Central Asia to parts of Eastern Europe. The theory suggests these were not drainage systems but components of a larger infrastructural network, possibly for pressure regulation or resource distribution. Liverpool Road Station did not need these underground systems to function as a railway terminus. Yet they were already there, built and waiting beneath the ground when the first rails were laid. The official history celebrates Victorian innovation. The foundations suggest Victorian adaptation. I had expected experimental chaos. Early railway development should show improvisation, false starts, and gradual refinement. Instead, across 3 of Britain's earliest railway stations, I found consistency, uniformity, and preparation. The subsurface systems do not behave like experiments. They behave like infrastructure inherited from a prior technological framework, one sophisticated enough to standardize components across hundreds of miles. The buildings above present themselves as inventions. The systems beneath suggest adaptations. Gare de l'Est officially opened in Paris in 1849, and it was designed by François Duquesne. The Parisian archives contain early photographs showing subsurface iron hatches nearly identical to those at Euston, with the same diameter, the same bolt patterns, and the same surface finishing. A renovation report from 1885 stored at the Bibliothèque Nationale mentions removal of hydraulic components no longer understood by station maintenance staff. The phrasing is careful, almost apologetic. Not broken components, not obsolete technology. Components no longer understood. I examined construction photographs from 1847. The subsurface infrastructure was already substantially complete when work began on the above-ground terminal building. Workers are visible installing platform supports into pre-existing foundation systems, connecting new structural elements to older underground networks. French railway engineering journals from the period make no mention of these subsurface hydraulics. The official construction narrative describes foundation work as routine excavation and bricklaying, but the photographs show vaulted chambers, pressure-sealed hatches, and iron piping of sophisticated design. Maps from the early 1800s, including French military atlases from 1805, still labeled vast Asian territories as Grande Tartarie. Some Tartarian researchers argue that European rail expansion did not create new transport corridors, but followed pre-existing infrastructural routes laid down by an earlier civilization whose works were systematically repurposed and reattributed. At Gare de l'Est, the 1885 renovation systematically removed the underground hydraulic systems. The removed components were not catalogued, were not stored in museums, and were not studied by engineering schools. They were simply taken out and disposed of. Paris may not have built these systems. It may have inherited them, used them for a time, and then quietly eliminated them when they became inconvenient reminders. Russia complicates the narrative in ways that Western European examples do not. The transparency is different there, perhaps because Tartaria remained on Russian maps longer, perhaps because the infrastructure was too extensive to completely obscure. The Moscow to St. Petersburg Railway, completed in 1851, was hailed as a triumph of imperial engineering. Yet construction diaries from Pavel Melnikov, the chief engineer, refer to ancient embankments of unknown origin being reused for rail beds. Ancient embankments. Engineering reports from the 1840s discuss infrastructure that was supposedly built within living memory. Early photographs from 1852 show the completed rail line running along elevated earthworks of remarkable straightness. These embankments extend for dozens of kilometers with minimal deviation, maintaining consistent width and grade across varying terrain. Pre-railway maps from 1820 show the same embankments already present, labeled simply as old transport routes. Beneath the tracks, visible in maintenance photographs from 1855, are stone-lined channels that were sealed shortly after the railway's completion. A notation in Melnikov's diary from August 1851 states that subsurface conduits of unknown purpose were filled with earth to prevent water accumulation. Russian cartographic history is instructive here. While Western European maps gradually replaced Tartaria with more specific regional names starting in the late 1700s, Russian maps continued using the term well into the 1850s. The 1786 General Map of Russia labels enormous territories across Siberia and Central Asia as parts of Tartaria. Some researchers argue this openness was not ideological but practical, because the Russians encountered so much pre-existing infrastructure during imperial expansion that denying its existence would have been pointless. The Moscow to St. Petersburg railway construction budget shows significant cost savings attributed to utilization of existing earthworks. The savings were substantial, roughly 30% of projected foundation costs. Russia inherited more openly than Western Europe, but it explained no more clearly. The embankments were ancient, the channels were unknown, the infrastructure was simply there, facts presented without interpretation. The Pennsylvania Railroad's early workshops, completed between 1846 and 1857, display features that should not exist in American industrial architecture of that period. The United States was still developing its railway network and still importing European engineering expertise. Yet photographs from 1850 show workshop buildings in Altoona with oversized arches, buried chambers, and precision iron plates matching those visible in European railway stations built years earlier. The architectural language is identical, despite an ocean separating the construction sites. An 1851 engineering journal described the Pennsylvania Railroad's foundation work as proceeding with unexpected efficiency due to favorable ground conditions. The phrasing mirrors Brunel's letters about Paddington, noting integration with existing conditions. Beneath the workshop floors, visible in a cross-section, drawing from 1853, are brick-vaulted chambers of the same dimensions seen at Paddington and Gare de l'Est, 2.1 meters in height, 3.8 meters in span, and 0.6 meters wall thickness. The precision of replication across continents suggests standardization that should not have been possible in the 1850s. American industrial journals praised the Pennsylvania Railroad's speed and innovation, but the photographs show no transitional designs, no experimental phases. The subsurface infrastructure appears fully formed from the beginning. Some Tartarian researchers argue this pattern, identical architectural solutions appearing simultaneously across multiple continents, indicates global reuse of standardized infrastructure. The alternative explanation requires accepting that separate engineering teams, working independently, somehow arrived at identical subsurface designs within the same decade. In 1895, during workshop expansion, the Pennsylvania Railroad filled many underground chambers with concrete. A maintenance report notes the decision was made to simplify foundation systems and eliminate redundant structural elements. The patterns cross oceans, the systems replicate with precision that defies the technological limitations of the era, and in every case the official history celebrates local genius while the physical evidence points toward inheritance. Berlin's Anhalter Bahnhof, completed in 1880, arrived later than most major European railway terminals. By that point, rail engineering should have been well established and thoroughly documented. Instead, the station reveals the same troubling patterns. Construction photographs from 1879 show iron components cast to tolerances matching those seen decades earlier at Euston and Paddington. The circular floor plates, the pressure hatches, the subsurface fittings, all identical in design despite being manufactured by different foundries in different countries. A factory log from Borsig-Werke, the primary ironworks contractor, mentions molds of unknown original specification provided by the Railway Commission. The phrase appears in 3 separate entries during 1878, unknown specification, as if the molds themselves predated the factory's understanding of their purpose. I examined component drawings archived at the Deutsches Technikmuseum. The subsurface iron plates show bolt patterns with 8 mounting points arranged in a precise radial configuration, each hole drilled at exactly 45 degrees from its neighbours. This pattern appears in British railway photographs from the 1840s, in French examples from the 1850s, and in American samples from the 1860s. The same design reproduced across 4 decades and 4 countries. During renovations in 1912, station maintenance crews removed many of the subsurface components. A work order describes the items as obsolete pressure fittings no longer connected to operational systems. The removed components were not catalogued as historical artifacts, they were scrapped. The iron is identical across decades and continents. The omission is equally consistent. Every renovation includes the quiet removal of these systems, the careful elimination of evidence that something standardized and sophisticated existed before official railway history begins. In Berlin, as in London, as in Paris, as in Philadelphia, the pattern holds. Precision components appear in the earliest railway construction, serve some unstated purpose, then disappear during later renovations. Turin's railway yards, developed starting in 1861, overlay earlier fortification earthworks visible in pre-railway maps. The city's star fort shows the characteristic geometric layout with angular bastions radiating from a central point. What struck me examining an 1850 survey map was how perfectly the later rail alignments followed the bastion angles. The tracks do not merely avoid the old fortifications, they mirror their geometry, running parallel to bastion walls, curving at exactly the points where defensive earthworks change direction. Tartarian researchers have long argued that star forts were not purely military, but infrastructural, components of pressure and flow systems, their geometric precision serving hydraulic rather than ballistic purposes. The angular layouts, the massive earthwork volumes, the underground galleries, these features make more sense as parts of a distribution network. At Turin, the rails follow those ancient flows. Platform positions align with former bastion points. Underground passages visible in 1862 construction photographs connect railway facilities along routes that match the old fort's tunnel network. A construction report from 1863 mentions adaptation of existing stone channels for railway drainage systems, but the channels predate the fort's official construction date. Maps from 1640 show the tunnel network already present, with the star fort built around it. Geometry is too precise to dismiss. Railway engineers, supposedly designing modern transport infrastructure, laid their tracks along paths determined by earthworks whose original purpose had been forgotten. Across Tartarian territories from the Urals to Central Europe to parts of Scandinavia, star forts appear with remarkable consistency, and wherever railways later developed, they followed these ancient alignments. Turin's rail yards did not create new geometry. They traced older patterns. Vienna's railway stations, developed during the 1860s and 1870s, contain sealed pressure chambers beneath their platforms that appear in maintenance logs as legacy systems requiring isolation from modern infrastructure. Legacy systems in buildings barely a decade old. An 1870 maintenance report describes chambers beneath Suedbahnhof platform level, sealed due to incompatibility with current operational requirements. The chambers measured approximately 4 meters in diameter, lined with brick and sealed with iron plates matching those documented at earlier stations across Europe. Photographs from 1869 show these chambers during initial construction. The brickwork displays the same curved precision seen in hydraulic systems, smooth surfaces, uniform mortar joints, and careful attention to pressure-bearing capacity. These were not simple storage spaces, they were designed to contain something under pressure. But contain what? Vienna's railways ran on steam locomotives burning coal. No pressurized systems beyond the locomotives themselves should have been necessary. During an 1885 renovation, workers broke through sealed brick walls and found the chambers empty except for iron piping of unknown purpose. A foreman's note records removal of obsolete distribution systems, origin uncertain, and no current engineering staff familiar with operational intent. Obsolete systems were removed, the piping was removed, the chambers were filled with concrete, and the official record moved on. The term legacy system implies inheritance from a predecessor, but Vienna's railways had no predecessor. Unless the legacy predated industrial railways entirely, infrastructure from an earlier period repurposed for new uses, then quietly eliminated. Predecessor remains unexplained. Some researchers examining regions historically mapped as Tartaria point to Vienna's location as significant, positioned at the western edge of territories labelled Tartaria Europea on 18th century maps. Tartaria appears on those maps. The sealed chambers beneath Vienna's platforms tell the same story as those in London, Paris and Berlin. Something was already there when the railways arrived. Between 1880 and 1920, renovations across Europe and America systematically removed subsurface railway infrastructure with remarkable consistency. Official reports use vague language: obsolete, redundant, unknown, legacy, incompatible. These terms appear in renovation documents from London to Vienna to Philadelphia to St. Petersburg, always describing the same types of infrastructure: pressure chambers, hydraulic systems, sealed passages, precision iron components, and always recommending the same solution: removal and filling with concrete. An 1892 renovation of London's King's Cross station included sealing of subsurface chambers no longer required for operational purposes. The chambers had been accessible since the station's 1852 opening. For 40 years they had remained part of the infrastructure. Then, suddenly, they needed to be sealed. At Gare du Nord in Paris, an 1889 modernization project removed hydraulic regulation systems of uncertain origin. The systems had functioned for decades. Their removal was not motivated by malfunction, but by uncertainty about their purpose. In Boston, an 1895 renovation noted the disposal of pressure vessels and associated pipework predating current engineering standards. The vessels were intact, not corroded. They were removed because they predated standards, suggesting they had been built to different, perhaps older standards. The pattern is systematic. Across 2 continents, across 4 decades, railway authorities made coordinated decisions to eliminate subsurface infrastructure they did not understand. Not to study it, not to preserve it, simply to remove it and fill the empty spaces with concrete. Silence replaces explanation. The renovations proceeded quietly, documented in brief maintenance reports that offer no technical drawings, no detailed descriptions. By 1920, most major railway stations had been renovated at least once. The subsurface infrastructure visible in the 1840s and 1850s photographs was largely gone. What had been eliminated was not malfunctioning technology. It was functional infrastructure whose presence contradicted the narrative of continuous industrial progress. Maps tell their own story, one of gradual disappearance rather than discovery. Guillaume de Lissal's 1720 Carte de Tartarie shows enormous territories labelled with precision, illustrated with cities, and marked with transport routes. The geography is specific, not speculative. By 1750, the term still appears across European atlases. D'Anville's maps, Homann's atlases, Russian imperial surveys all include Tartaria as a recognized territorial designation, sometimes subdivided into Tartaria Magna, Tartaria Europea, Tartaria Deserta. But as the 19th century progresses, Tartaria fades from cartography, not because the territory changed, but because the naming did. Regions previously labeled Tartaria become Siberia, Central Asia, Mongolia, designations that emphasize emptiness and absence of infrastructure. The renaming coincides with railway expansion. As European and American rail networks spread during the mid-19th century, incorporating regions previously mapped as Tartarian, the old territorial names disappear from official cartography. Yet infrastructure remains. The precision earthworks, the subsurface systems, the hydraulic networks. These physical remnants appear wherever railways developed. An 1887 Russian railway survey mentions utilization of ancient stone foundations in territories formerly labeled Tartaria on earlier maps. The foundations are ancient, the maps are current, and the connection between them goes unacknowledged. The infrastructure outlasts the names. Earthworks persist when cartographic designations change, and as railways build atop these older systems, incorporating them into modern transport networks, the original builders vanish from historical memory. By 1900, few maps still showed Tartaria. The territory had been subdivided, renamed, recontextualized, but the rail networks built during those decades followed paths that had been marked on older maps. Names disappear more easily than infrastructure. You can redraw a map overnight. Removing massive earthworks requires decades of systematic effort. The railways helped complete what the maps began, the erasure of Tartaria from official memory, not by destroying the evidence entirely, but by incorporating it so thoroughly that its origins became invisible. Standing in the archives with photographs spread across the table, a hypothesis forms. It requires careful statement because it challenges foundational assumptions. Some researchers propose that Victorian builders inherited a global infrastructural skeleton, Tartarian in origin, and wrapped it in brick, iron, and narrative, not built from nothing, repurposed from something older. The evidence supporting this hypothesis is architectural rather than textual. Identical subsurface systems appear across continents from the 1830s to the 1850s. Precision standardization exists before international engineering conferences became common, and systematic removal follows in the late 19th century renovations. These patterns suggest inheritance rather than invention. Consider what parallel invention would require. Separate engineering teams in Britain, France, Russia, America, and Prussia would need to independently develop identical solutions to problems they were not trying to solve. Railway terminals do not need pressure-rated chambers beneath platforms, yet these systems appear consistently in the earliest railway construction, then vanish during later renovations. The Tartarian hypothesis offers a simpler explanation. Builders in the 19th century found existing infrastructure and adapted it. Precision iron plates became floor covers, hydraulic chambers became storage spaces, transport corridors became railbeds. The approach is practical, not mystical. Maps support this reading. Tartaria appears in cartography until railways begin spreading across the same territories. As rail networks incorporate existing earthworks and subsurface systems, the territorial designation fades from official records. The infrastructure remains, but its origins are reattributed to Victorian innovation. This is not conspiracy, it is narrative construction. Every civilization tells origin stories that emphasize its own innovations. The Victorian era needed to believe it invented everything from scratch. Acknowledging inherited infrastructure would complicate that story. So the infrastructure was absorbed, repurposed, and eventually eliminated during renovations that simplified what could not easily be explained. By 1920, most major railway stations had been modernized, and their subsurface anomalies were removed or sealed. Erasure became routine, The Victorian shell hypothesis does not prove Tartaria existed as a unified civilization, but it documents a problem, a gap, between what official history claims was built and what physical evidence suggests was inherited. I return to Euston now, decades after those first renovations. The station has been rebuilt multiple times. The original 1837 structures are mostly gone, demolished during modernization in the 1960s. Euston has been reshaped repeatedly. The iron circles I found in the 1846 photograph no longer exist in physical form. The platforms have been repoured with concrete and the subsurface chambers have been filled or demolished. The iron elements are gone, but the spacing remains. If you measure the support columns in the current station, they align with the positions of those circular covers visible in the Victorian photograph. The geometry persists even though the original elements have vanished. Ghost geometry describes patterns that survive structural replacement because they are dictated by what lies beneath. I examined foundation surveys from the 1960s renovation. Engineers noted unexpected difficulties excavating certain areas, and they reported encountering older foundation systems requiring careful removal. Those systems were older than the Victorian station itself, old enough that their purpose could not be determined from their structure alone. Foundation traces were documented and then cleared. These older systems were removed, the renovation proceeded. The official record describes only the new construction, not what was cleared away. Removed is how evidence disappears from the archive. This is how erasure works, not through dramatic destruction, but through routine modernization. Each renovation strips another layer of evidence, until finally, only photographs remain. I think about the 1851 maintenance ledger's instruction, sealed underfloor access plates, not to be reopened. Someone knew those chambers were there, someone decided they should remain closed, and someone later decided they should be filled with concrete and forgotten entirely. The decision was not malicious, it was practical. The chambers served no apparent purpose in modern railway operations. They raised questions that had no comfortable answers. Easier to remove them, easier to forget. The official story says we built everything from scratch during the Victorian era. Innovation creating modern infrastructure through engineering genius. The ground beneath the rails tells a quieter story, preserved in photographs, maintenance logs, and the persistent geometry of structures that do not align with their supposed construction dates. In the archive, I study the original 1846 photograph again. The circles are small in the image, easily overlooked. Perfect, identical, unexplained. Sealed chambers, removed systems, identical components appearing across continents before international standardization existed. Renovations that erased rather than preserved. Maps that stopped showing Tartaria precisely when railways began expanding across formerly Tartarian territories. This investigation does not prove Tartaria existed as a unified civilization. It cannot demonstrate conclusively that Victorian engineers inherited, rather than invented, their subsurface infrastructure. But it documents a problem, a gap between record and reality, a systematic pattern of erasure that suggests something uncomfortable about our accepted historical narrative. The evidence accumulates quietly. Precision beyond period technology, standardization before engineering conferences, identical solutions across impossible distances, systematic removal during renovations, archival silence surrounding subsurface infrastructure. And once you see it, the pattern becomes impossible to ignore. In London, Paris, Berlin, Vienna, St. Petersburg, Philadelphia, Turin, different countries, different decades, different engineering firms, but the same subsurface geometry, the same precision components, the same unexplained chambers, the same careful elimination during modernization. Tartarian researchers have pointed to this pattern for years, arguing that our industrial revolution built atop remnants of an earlier, more sophisticated civilization. The hypothesis sounds implausible until you measure the symmetry, examine the tolerances, notice the impossible standardization. Then it becomes not proof but possibility, a shadow that will not disperse no matter how bright we make the official historical narrative. The circles beneath Euston's floors are gone now. Their spacing remains visible in support column positions, dictating geometry that modern engineers follow without understanding why. Ghost infrastructure, inherited rather than invented, repurposed rather than built. And wherever you look closely at early railway construction, beneath the Victorian narrative, beneath the industrial triumph story, you find traces of something older, something that does not fit the timeline we have been taught.